to get the scene CSV of ABB2400 6-axis robot. On the screen you can see ABB2400 6-axis robot, which IGS file given by ABB, Mr. Chen. We developed this robot very early, 5 years ago. But today we found ABB2400 robot is not the normal 6-axis robot. You can see a bar and here connect to this joint and this joint. Another bar connect to the component 3. So we need additional calculation in our VC++ 6.0 program to handle those object movements. The IGS file given by ABB totally are 13 files from 2400-1 IGS until 2400-13.IGS. The CSV file created, especially the attachments, we have to analyze the structure of the 6-axis robot before filling the CSV file. We open right now. 2 computers are opened. One is the one display in front of us. Another one is a notebook beside me. The notebook opened the ABB2400 CSV file, so we can see together and to see which component is which. Right now, I demonstrate the movements to show the connection about the bar. On teaching mode, on join mode, the J1 rotating the left hand rule. The J2, you can see as J2 move, the connection bars will moving as well. J3, from J3 you can see the bar goes down and this bar rotating. The object moving is calculated inside the VC++ 6.0 program, while the rest objects is controlled by 3-axis acceleration cars API automatically. J4, J5, and J6, and to show the Cartesian coordinate system, x minus, y plus, y minus, z plus, z minus, Rx plus Rx minus Ry plus Ry minus Rz plus Rz minus. So you can see the variation about the additional connection bar. In our demonstrations, we'll show the program written the variation of this object and this object. And we found from object 2 to object 8 all be influent. So many objects program written on VC++ 6.0 program. So the better solution is just to forget this object and this object and leave ABB2400 robot as a standard 6-axis robot. We'll show this way later. Right now, let's analyze the structure of this 6S robot new to clear the screen. IGS X model to get the foundation first. The foundation we started from 1 until 13 of the given IGS. The table, the file folder is D ABB2400 D ABB2400, and the X file started with 2400 and a dash. We changed the folder to CMS GAC and the data because we try to see the original one. The original one is CMS GAC data and the 2400-start X from 2400 start 1 until 2400-13.x. You can see in here we started to show the first one, 2400-1.x. This is the foundation of the robot. The next connect to it. 2400-2.IGS. The model shown just like this. And the third IGS give the model, okay, shown on here. Which are connecting piece. We have two additional pieces. One is this one, another is a longer connected to component 4. So 1, 2, 3. Then we open fourth IGS file 2400-4.x. And then let's see what is the 2400-5. 5 is the connector rod. So and to see 6 2400-6.x. is the main component of a 6S robot. So this one connect in here and here and join together in this point, as this one rotating down and this joint will up, and the bar will lift this joint up, and the rotation will be happen about this bar. Then how about the 7 2400-7? Okay, 7 is a main component about the J5. And how about the A 2400-A? A is, you see in here, is J6. And how about the 9? 9 is the component rotating around the x-axis. It seems the whole robot's already on the screen, started from 1 until 9. So how about the rest, 10, 11, 12, and 13? Okay, let's see. What is the 10? Is the ABB characters. And how about the 11.IGS? Is ABB as well, written together. And how about the 12? The 12 is the motor. This one. And the 13 is another motor on the other side. Let's see in here. So after this analyze, if we try to do a new translation, the IGS file into X file and feeding CSV table and run this robot as the standard 6S robot to remove this component and this component. Then we know we have to let object 12 and 13 to join the object 2. Actually, in our definition is J1. ABB characters should join this component. Okay, let's start it. The translation from IGS1 until IGS13 to translate this IGS into SolidWorks, and then to do the normal separation from foundation 0 until the last J6 components. We go to SolidWorks to do this translation. The same, we open O file. We have prepared the data at the ABB2400 to translate the input IGS file 2400-1 until 2400-13. We started from the first one, 2400-1, and open it. The program is running. Active. Okay, after the foundation shown on the screen, we have to see if the given geometry is correct. We just show the front placement SZ, and to see the original at the center and the bottom of the foundation. So the YZ is correct, located just the same as CMS CAPP Cartesian coordinate system. So we change nothing. And the color, no change as well. So we direct to output PRT file and IGS file. According to the naming method, this one, although is 2400-1 IGS, but we named it as foundation as 0. We show the previous demonstrations CSV file, which is robot ABB2400. Okay, open it. You can see robot ABB2400 CSV file. The mark here is 4. It's mechanism 4. The mechanism 3 in our system is ABB2600 robot. For ABB2400 robot, we give the mechanism 4 as this style, 6-axis robot. The mechanism 3 and the mechanism 4 is specified for these two special robots, not like mechanism 2 you can use for any 6-axis robot. As we just talking about, we have to remove 2 additional connection bar to let ABB2400 handled as the normal mechanism 2. Right now, the demonstration is going on. So we save this one as J0 as foundation. So we save another file, save .prt first, and we name it R4B0. 4 is mechanism 4. B is a robot. R4B0 is foundation. And save it. And then we save another file. The type is IGES. The file name is R4B0.IGS. Save it. Okay, we continue to J1. How to do it? Just close the old file and open an old file. The type is IGS from the ABB2400 folder. And the second one is 2400-2 IGS. Translate into the screen. Active. Okay, we get a component already. Then we save the PRT file. Save another file as PRT. The name is 2400. The name is J1. R4B1. 1 means J1. 0 means foundation. Okay. The first step, just save one by one. In here, R4B is combination already. You can see from R4B0 1, 2, 3, 4, 5 until 6, no more. So the program actually running is 2400-1.IGS. Translate into .prt and save the PRT file give another name. We call it 2400-1R. No change anything. That means 1 become 1R until 13R. After that, we can insert this component on the screen to get the assembly of the machine, and then use the whole machine to do the combination to get R4P0, R4P1. R4P1 have to add 2 additional motor, which is 2400-12 and 2400-13. Okay, right now we try to do the assembly which coming from the -1R until -13R. Okay, how to do the assembly of the 6S robot? We close the file first, no saving, and open an assembly webcam file. Use assembly insert component function to insert 2400-1R first and open it at its original position. While doing this insert component, we can still see the assembly of the component, and insert 2400-2R at its original position, and insert 2400-3R. Just the same like previous demonstration about the assembly of the robot. So 1, 2, 3 already. So input 2400-4R and insert 2400-5. So the object 3 and object 5 has to be removed. That is, this one and this one will remove as doing this robot as the normal 6S robot for the demonstration. So 5, then insert 6, 2400-6R. And -7R and -8R and -9R and the rest 4 is not very important. You forget or not, depends on the user, because -10 is the ABB character putting on here on top of object 9. insert 2400-10 is ABB as well. Oh, we got a 210, 8, 9, 10. So remove one. And insert 11 is a model. Oh, 11 is character as well. 10 and 11 is character written on the same position. And 12 and 13 is a model. This model at this side. The last one, 13, located at the other side of the row bar. So 1 until 13 is the original given IGS file. This is the assembly of ABB2400 row bar. We save it. Save another file. Use style assembly.asm. The file name give 2400 and another org means original data, and save it. We save this one so we can do the combination. First of all, we do the foundation, pick it. The 1R is the first one, so we remove the rest to save this one, the basement PRT file and IGS file. So we have to remove from the second to the last. How to do it? Just press the left button at the second and move the cursor to the last one, and press the shift key of the keyboard together with the left button of the mouse. So press the delete key of the keyboard and choose delete all. Thereafter, only the basement on the screen. Then we save the PRT file by using save another file function. The type, choose .prt type. The name, give roba RB roba 4 mechanism 4 foundation 0 R4B0 to name it. So we save R4B0.prt first. Then we save another file, give the type IGS, and the file name the same, R4B0.IGS. Okay, after the first one, then we trying to do the J1. This is J0. The J1, how to do it? We just close the file, no saving, and open the assemble. Assemble is 2400 original org, and then to pick the second. The second is this one. Is 2R, but we have to join this one 13 and this one 12. So 2, 12, 13 left on the screen, the rest deleted. So we started from this one until this one. This is the majority. and then put a cursor on the first one and press the control key of the keyboard together with the left key of the mouse. And then press the delete key of the keyboard and choose delete all button and left these three parts on the screen, and then save totally as J1. Save a new file. The first save the .prt file. The file name, this is J1. We give R4B1 because it is a J1. PRT, save it. And then we save IGS file. Use save another file function. The type give IGS. The file name the same as previous R4B1.IGS. Okay, the J1, okay. Then to do J2, close the file, no saving. Take the original sample 2400 original on the screen. This time we do the J2. The J2 is this one. The J1 rotating around 001. The J2 rotating around the y-axis. So this one is J2. We have to remove the rest parts. We started from the majority, from this one until the last, and these three pick one by one. Okay, after this, press delete key of the keyboard and remove all. Then we save PRT file and save IGS file. Save another file as PRT file. We name it J2 R4B2. Save it. Then we save, use another new file. We save .IGS file. The file name the same, R4B2 IGS. The main purpose is to get IGS. This IGS can be translated into X file inside Polytrans, the program. So we just continue to get to do one by one until we get R4B3.IGS, R4B4 IGS, R4B5 IGS, R4B6 IGS. Then we have to do the tool. The tool, if we still use the original tool, the welding tool of CO2, a micmac. Then how can we do? We just remove this one and insert the 6th join, the 6 J6. J6 is R4 B6 PRT file on the screen. And then to mark the point of the flange in front of the J6, we just put the cursor on the edge an orange circle highlight on the screen. We simply press the left button to get the center of the circle. Write down before using. The X940 Y0 Z1455. Okay, then we adopt by use the insert component to choose the welding tool from the original D Eurotech to get the PRT file as R tool and open it at its original point. What is the original point? You see, the original point is at the center, the original points of Cartesian coordinate. Then we have to let this point move to the TCP original point. The original points of TCP, we know it is 940 0 and the Z is 1455. So how to let this one move to this position? How to do it? But first of all, we have to remove the fixed character in front of the R tool by pressing the left button of the mouse and choose floating. The fixed characters being removed. And then how to move this one to here? Selecting first and then use move the component function and use from delta XYZ and the keying X940 Y remain 0 and the keying delta X 1455 and OK. You can see the tool go to the origin TCP points join together. So the location of the tool is at the right position. After that, we save the tool PRT file and IGS file. How to do that? Right now, two components on the screen. We have to select the J6 and press the delete key of the keyboard to remove it and left the tool on the screen only. Then we can save the PRT file by using save another file the type, choose .prt, and the file name, give ABB4 tool, and save it. Then we have to save .igs file by choosing save another file. The file type, choose IGS. The file name, give R4B tool. The save R4B tool.igs. Save it. After saving, we can see the whole IGS file are prepared. What is prepared? The tool R4B tool IGS, R4B6 IGS until R4B0 IGS. These 7 IGS files prepared. So the job of SolidWorks finished. Then we leave SolidWorks, go to Polytrans to translate this 7 IGS file into X file to prepare the IGS file for the CSV table. So we go to Polytrans to do the foundation R4B0.igs first by using translate, using import 3D geometry. Select coming from IGS V50 via Okino ASCII file function, and to give the correct folder ABB2400, the ABB2400, and the IGS file as the style. The first one is R4B0.igs. Open it. OK. Yes. Start Scene Optimizer. Start. Yes. We can see the foundation on the screen. Then we save the positive X file by using export 3D geometry, the rest file style. The positive left these two open, the rest be picked. OK. The folder D ABB2400, the positive of the foundation, we give the name R4B0A and save it. The negative X file of the foundation by export 3D geometry direct S file. We have to pick reverse orientation of all polygon and normals, and then pick flip polygon normals. OK. The folder correct. The negative we use B to save the X file as R4B0B.X and save it. The positive A and the negative B saved. Then we have to do the combination about the positive as well as the negative. How to do it? Use reset scene negative to clear the screen of the Polytrans first. Then translate, import 3D geometry, the rest file. Choose the correct folder. From D ABB2400. Input R4B0A, the positive .x first. OK. Yes. R4B0A in. And then the negative by import 3D geometry, the res file. R4B0B.x. Open it. OK. Yes. The negative R4B0B in as well. Then combine it and save it. Save it out. Save them out. By using export 3D geometry, the res file. We save the positive only. OK. The file name purely given R4B0.x. OK. Then, by the same method, import IGS file and save the positive R41A.x and save the negative R4B1B.x, and then use VSync to clear the display on the screen, and use import X file R4B1AX in, and then use import 3D geometry R4B1B.x in as 1A and 1B display on the screen. Then remove the screen. Before removing the screen, use export 3D geometry the res file, output R4B1X. Then use VSync to remove the display on the screen. By the same way, we can get R4B2X, R4B3.x, R4B4.x, R4B5.x, R4B6.x, and the last one, the tool, R4B2.x. After these 7 IGS files translated into X file, then we have to move this 7 S file into CMS CAPP, our data folder. That is the R4B2.x, R4B6X, R4B5.x until R4B0.x. This 7.x file has to be copied and moved into CMS GAC data folder. After move this 7x file into the data folder, then we're doing the actual speech about how to generate the CSV table. So go to the CMS GAC data. To see a CSV table, we copy a CSV file and then rename it as R4B2400 new. Then we see we change all the S file and the correct pivot position. Then we press twice of the left key of the mouse to see inside of the CSV table. We see the started from the S file. The foundation R4B0.x filled in. Give the name mesh 0 object 0 attached to itself 0 object. The first J1 R4B1.x give the name mesh Z1, the object name object 1. Object 1 attached to object 0 attached to the foundation. The J2 R4B2X give the mesh 2, object 2 attached to object 1. The J3 R4B3.X give the mesh name 3, object name 3, object 3 attached to object 2. The J4 R4B4.X give the mesh name 4, object name 4, object 4 attached to object 3. The J5 R4B5.X give the mesh name 5, object name 5, object 5 attached to object 4. The last one, the J6 R4B6.X give the mesh name 6, object name 6, object 6 attached to object 4, object 5. Next one is to define the tool. R4B tool.x give the mesh 7, object name 7, object 7 attached to object 6. The rest is the dummy.x6 to define from axis 1 until axis 6. To define the limitation of J1 until J6, the positive and the negative rotation degree. The last three is the standard RGB arrow by sequence naming is mesh 14 until mesh 16, object 14 until object 16. The attached tool of the RGB have to give the object number the same as the tool. The tool is object 7 attached to object 6, so RGB has to attach to object 6 as well. Okay, now we continue to see the table. These parts. Before seeing these parts, we have to see the mechanism type 2 written on here instead of number 4, because we move the two additional connection bar. Use a standard 6-axis low bar for the demonstration. So the 2 written here is correct. Doing the relationship between the virtual machine and the physical machine, we started from the motion control car, the first one, axis 1 of the motion control car. The J1 is controlled by the axis 1. The J2 is axis 2. J3 is axis 3. J4 is moved by the fourth axis of the motion control car. The J5 is controlled by the fifth axis of motion control car. The sixth component is controlled by the sixth axis of the motion control car. The first axis translocate, which is 2. 2 means it's a rotation. It's rotation axis. The J1 rotation about 001, N10, N20, N30, N31. 001 is point to sky. It's positive Z direction. It's rotating about the Z axis. For the rotating, we have to define which pivot point this axis rotating around. Rotating about Z axis, then we can forget the Z pivot coordinate. It could be anything, but X pivot, Y pivot written in here 00, we have to use SolidWorks to make sure it is these two value is correct. So we go back to the SolidWorks to remove, to clear the screen, and to insert the component. To insert the first PRT, the basement, the foundation R4B0, and open it at its original point to find the rotating coordinate. But this is polygon. You cannot find the rotating points from these components. So we insert the one on top of it. That is RB1, and put it back at the original position. And fortunately, we have the circle to get the center of the rotating. We just press the cursor on the edge to get a highlight orange circle, thick circle. And how to get the center of it? Just press the left button of the mouse. The center will written in here 00. Forget the Z. So 00, and go back the CSV table to see here 00. So this is correct for the first axis. Now we go to the second axis. The second rotating around Y-axis 010. So leave the Y pivot point anything. We have to make sure X pivot 100 and the Z pivot 615 is correct. So we go back to SolidWorks to see the rotating axis. Okay, as the circle highlight, we simply press the left button of the mouse to see X 100, Z 615 to check 100 615. So the second is okay. So how about the third axis? The third axis rotating around 0, 1, 0, rotating around y-axis as well, is rotating too. So leave the y pivot be anything. We have to make sure S pivot be 100 and the Z pivot be 1320. We go back to SolidWorks and insert R4 B2 at its original point, and to see the pivot points X and Z is the same as the CSV table or not. By pressing the left button as the circle highlight, okay, you can see 100 1320 100 1320. So the third is correct. Then go to the first axis. The first axis rotating around 101, rotating about x-axis. So we forget the S pivot point coordinate. Just emphasize the Y pivot point and the Z pivot point. If the same, like the CSV table, so we go back to SolidWorks to adopt the next component. Insert R4 B3 and open it at its original points. But it is impossible to get the data here, and this one cannot get the center of the rotating points. So we insert the component in front of it, that is R4 B4. Insert R4 B4 at its original points. Oh, we see the wrong way. We have to see this point, so we hide this one to see if from here we can get it or not. Oh, this is not a circle. We cannot get the pivot point from here, so we still have to see this component and hide this component, and to see the pivot point from the circle at here. As the circle highlight, just simply press the left button of the mouse to see this Y and this Z is correct written on the CSV table or not. So 01455 01455. So the first axis is correct. Continue to see the fifth axis. The fifth axis rotating around the y-axis. So N1 0, N2 1, N3 0. Rotating around the y-axis, we leave y pivot value be anything. We have to make sure X pivot 855 and the Z pivot 1455 is correct. So we go back to the SolidWorks to see the join here. And rotating around here, but this is polygon, impossible to get the value. So how about in here? Oh, it is a polygon as well. We cannot get a center in here. So how can we do? We cannot get a center from this component. Then we adopt the J5 component, R4 B5, to see if we can get from R4 B5. So we insert R4 B5 at its original point, and to hit R4 B4 to see if we can get from here. Still, it's polygon. We cannot get the data center from here or from here. So maybe we need another CAD system to get a center, or we have to find a way to get from this joint. How to do it? We can put the cursor on top of the surface and press the left button of the mouse and highlight and choose normal to function. So we will see normally to see the surface, and to see in here the coordinate is x, z. So the center we get is s and z coordinate if we can get it, and enlarge the highlight circle. After that, we can use open sketch to draw a circle and open the sketch. Then we can use 2D function by 3-point arcs, and he write some statement written on the button, which is we have to choose 3 points to define a circle. We choose 2 points first, and then define a circle by 3rd points by drag the circle. So we define 2 points. Beta is the radius 2 sides. We started, suppose, from these points. The second, we go to the opposite way. Okay, it changes colors, so we press too much. Let's do again by press on top of it, press the left button of the mouse. Okay, we delete this one, sketch first. Then doing again by press the left button of the mouse and normal to the surface and enlarge it. And open a sketch. Open the sketch and choose 3 points to define a circle. and mark here. We started suppose from this point, and the second point, and the third, to mark, to define the radius. You can see the radius is 60.75 and the right side of the pen are equal to 60.75. 180 degrees is a radius. So this is correct. Then we press the right button to make sure of the circle, and we can survey 1, 2, 3 points to define the circle. And if you mark the center X, Y, actually Y is Z, XZ. So X is 855 and Y is Z. Z is 1455. To see our CSV table is correct or not, we open the CSV table. Okay, X pivot 855 correct, Z pivot 1455. So the fifth axis of the motion control cars pivot point is correct, defined. We go to the next sixth axis. It is rotating as well, rotating around the x-axis. So N1 is equal to 1, N2 0, N3 0. We know the flange, the 3, all very important. So we have to get the last J6 to find this 3 value is correct or not. So how to do that? We simply insert a component. The last component is R4B6 and put it back to the original and turn to see the edge of the flange and put the cursor on the edge to highlight an orange circle. To get the center of it, simply by pressing the left button of the mouse, then the center will be marked down here. So we see 940.01455 is the same or not as the CSV table. So S pivot 940, Y 0, Z pivot 1455. So all correct. Then we continue to see the tool. Translocate for the tool marked. The number should be 3, and S pivot 243.3, Y pivot 0, Z pivot -25, and then rotating R Y 30 degrees is all correct. The limitation 4, 5, 6 until 9. 4 minus 3 is 1. This one is defined the limitation of the first axis. We check this limitation positive and negative limitation from the DM of ABB2400 to fitting this position. Okay, after this, we go back to our system to check if the table is correct or not. Don't forget the name of the CSV file is R4B2400 new. Then we save it. Yes. Yes. The name R4B2400 new. Save it. Yes. And go back to our program. New to clear the screen and use scene input to choose the D folder CMS GAC. Data D CMS GAC data, and to adopt R4B R3. Where is R4B? Is not correct, so we have to change to D CMS GAC data. D CMS GAC data. Then we can find R4B, R3, R4, B2400 new. This is the file we just check, and open the old file. So it seems correct as to see the skin, the scene, these two bars being removed. But we still have to check the join mode, the S rotating, the parent and the children is correct, connected. J2, okay. J3, no problem. J4, J5, J6, it seems okay. And to check the Cartesian coordinate system, this is X, Y, the blue is Z. So X positive, you see this direction, X minus direction, Y positive direction, Y minus direction, go up and down. Z positive direction, go this way. Z negative direction, go this way. Then rotating, Rx positive, X positive, this arrow don't move. The thumb point to the red arrow direction, and the rest, the four fingers, show the turning direction. So it is correct, Rx positive. And how about Rx minus is correct as well. So how about Ry positive? It is correct, y minus direction is correct. So how about the RZ positive? It is correct. RZ negative direction. So the Cartesian coordinate system is correct as well. Then we show the robot setting by choose. Select 0 on screen. Then we can put the cursor on anywhere. Suppose on here. Choose. How to choose? By press the left button of the mouse. The second axis are chosen. So select 2 shown on here. So how to operate it? Just by press the left button of the mouse. Continue pressing and move the mouse toward the right. The second join will rotate around the positive direction, which is the left hand rule. As they move the cursor of the mouse toward the left part, the J2 will rotating around the negative direction. You can use this way fast to operate the join rotation. Then if we put the cursor on the select position and press the left button, the number will increase in 1. One press increasing 1. Suppose we select 7. The select 7 is the Cartesian X positive. How to operate it? By keep pressing the left button on the screen and move the cursor to the right. So the X positive, you can see the red arrow running to the right side along the yellow direction. As the cursor moves to the left, the red cursor will go to the opposite direction. The system will doing an inverse process of the mechanism. It will start it from the TCP points to calculate the correct position of these points, and then reverse calculate the rotating about the J6, J5, J4, J3 until J1, and doing the dynamic movement automatically for us. Okay, it seems okay. Then we're doing a practical usage of the robot. Our system has 3 ways to input data over GM code to run the CAN system. The CAN is the only important character to use the robot. We have 3 ways to input the data. First is DS file. DS file is coming from AutoCAD or some CAD system, which is 2-dimensional joins. That it means we can use DS file to do 2-dimension working. And then we can use any 3-dimension CAN system to generate GM code, 3D GM code. We can input 3D GM code. The tool can follow the path of GM code and to do the job, cutting job or whatever job for us. Another way is to input IGS file to get the 3D model on the screen. Then you can, along the edge, 3D edge, to cut the edge or grinding the edge or doing zigzag along the surface. Right now, just to simply display to demonstrate the DSF input for 2D working. First of all, we have to define the material position. In the robot system, there is no G14 function. We use material to define the position of the cutting material, which job is similar to G14 function of GM code. Right now, I defined X300, Y300, Z10 a square material, and a DSF file 1 will locate at the center of 300, 310 in the center of the material, and the center has original point. We will move minus 100 millimeters to the original of the Cartesian coordinate. That means from the original center of the Cartesian, move 800, Y move 200, Z move up 300 to get the original points of the raw materials original points. So okay, you can see 800s from the floor to go up Z 300s to get the original points actually at these points. Then for the second DSF parameter, to define the cutting speeds 100 millimeter per second, the left nothing, 0, left 0. The third DSF input, we get a DSF file named BTTY, a beauty, and adopt it. If the system at the CCS Cartesian coordinate system, then we can get, you can see the teach data is nothing. If right now in Cartesian coordinate system, if we use DSF input file and open a DSF file, the system will automatically calculate to show the picture on the screen, and you can see the data will be put inside the data area. The speed 100, just the same as we defined, 100 millimeter per second. The total data here is a head tail. The total data is 3086. Right now, we enlarge the picture and use run to show the cutting or grinding or whatever, or welding. This is a welding tool to do the welding, as running until the end of the demonstration.
我的脚踏遍天南和地北，你谁或是风